Yes, children, today we will start with P block elements, the next chapter. And you know already under periodic classification you have studied S block, P block, D block and F block. Now P block, where is it in the periodic table? It is between 13th group to 18th group. This is what you call it as P block because the electrons are filled up in the p orbitals of the atoms. Okay, so that is why they are called as P block elements. Like in the case of 13th group, the general electronic configuration is ns2 np1. That means one electron in the p orbital. Then in the 14th group, then one more electron is added, so it is np2. Then np3, np4, np5, np6. So this is because of this that they are all called as P block elements. Now what are the elements present in 13th, 14th, 15th and all? I have just shown here. It is boron, aluminium, gallium, indium, thallium. And in the 14th group you have carbon, silicon, germanium, tin, lead. Then in the 15th group, nitrogen, phosphorus, arsenic, antimony, bismuth. 16th, oxygen, sulfur, selenium, tellurium, polonium. Then in the case of 17 you have fluorine, chlorine, bromine, iodine, astatine. Then in the 18th group you have helium, neon, argon, krypton, xenon, radon. So these are the elements, right? Okay. Now it's good if you remember the names of the elements in each and every group. Funny ways also are there to remember things. Like you can write, you can think of ball, gain, tail. Then you remember what are the elements. Same way here. Funny ways of naming things are there. Us, se, ti, po. There are so many ways by which you can remember things. So these are all important. So if you remember what is a position, then it's easy for you to write anything, to understand anything. Now, what is the group oxidation state? For 13th group, it is +3. For 14th, it is +4. Then for 15th, it is +5, +6, +7, +8. Now, apart from this, what are the other oxidation states that these elements also show? Apart from +3, it also shows +1. Then apart from +4, it also shows +2. Same way, along with +5, +3 is also shown. Along with +6, you see here, it is showing +4 also, +2 also and -2 also. Then in the case of halogens, along with +7, they show +5, +3, +1 and -1. And in the case of 18th group, you know very well that they are noble gases. Neon and argon, they do not show any oxidation state, that is, they exist as individual elements. Whereas krypton and xenon, there are compounds of krypton and xenon which have been synthesized in the recent times. So krypton shows +2 and +4 and xenon shows +2, +4, +6 and +8. Like you have compounds of xenon like XeF6, XeF4, XeO3, like this compounds of xenon are there. So they exhibit these oxidation states. Okay, now when you consider these oxidation state, a very important topic, please understand this clearly. Down the group, 2 units less than the group oxidation state has been found to be more stable. Down the group, 2 units less than the group oxidation state has been found to be more stable, and this is what you call it as inert pair effect. Now, look here, I have shown along with +3, it is showing +1 also. This is 2 units less than the group valency. Along with +4, +2 is also shown. Again, it is 2 units less than the group valency. Again here, +5 and +3. So +3 is more stable down the group. Down the group, +3 is more stable. Down the group, +2 is more stable. Down the group, +1 is more stable. Okay. Now, if that is the case, What is the configuration? It is NS2NP1. So when you are subtracting 2 units, that means if you take out this, what is left behind is 1. That means this 1 electron alone is participating in chemical combination. These 2 electrons are not participating. From +3 to +1 means only 1 electron is lost. Which electron will be lost? Obviously from the outermost level, that is NP. So this electron is lost and this electron, these 2 electrons are bound. Okay. Now this is what you call it as inert pair effect. Now let us see further with respect to thallium. This is a 13th group element and atomic number is 81 and the configuration is xenon, then 4f14, 5d10, 6s2, 6p1. So this is the outermost electronic configuration, 6s2, 6p1, right? Now here the number of valence electrons are 3, 2 plus 1, 3. Sixth shell, if you consider, the number of valence electrons are 2 plus 1, 3. Now instead of +3 oxidation state, this thallium, it is exhibiting +1 oxidation state. Okay, so the 2 electrons of 6s, this remain reluctant to participate in chemical combination. Okay, so this pair of electrons is remaining inert. That is why the effect is called as inert pair effect. Okay, one pair of electron is remaining inert towards chemical combination. So it is called as inert pair effect. Now due to this inert pair effect, what do you find? Down the group, 2 units less than the group oxidation state has been found to be more stable. That is, TL is more stable in +1 oxidation state rather than +3 oxidation state. Right? This is 2 units less than the group valency. Group valency is +3 and 2 units less than that is +1. So you say that down the group 13, among the group 13 elements, the last element, that is thallium, will exhibit +1 oxidation state, which is much more stable than +3. Right? Now what is the reason behind it? Let us see that. Why it is showing 2 units less than the group valency? Why it is not showing +3? Okay, so that is what we are going to see now. Now in the case of thallium, what I showed, in the case of thallium, it is having 6s2, 6p1, right? Okay. Now the outer 6s electrons, they are bound to the nucleus because of poor shielding effect of the inner localized electrons. What are the inner localized electrons? In the case of thallium, the inner localized electrons include 4f14 and 5d10. Yes, now you know very well that this f orbitals and d orbitals, they are they show very poor screening effect. Now anything which shows poor screening effect, what it does? It makes the outermost electron visible to the nucleus. Is that clear? It's like you have I have explained this in the case of in periodic classification also. Say you have an wooden door and you stand here and somebody else is standing here. If there is a wooden door in between, the person who is inside will not be able to see who is outside. But if it is a glassy screen, then you will be able to see who is there standing outside. Is that clear? Now this glassy screen is similar to that of poor shielding. You are able to see the person outside. That means this is cloudy or this is transparent. Okay, same way this d and f orbitals also, they are more transparent. So outer electrons are experiencing the nuclear attraction. These are the outer electrons and they experience the nuclear attraction. With the result, what will happen? The electrons, outer electrons are bound to the nucleus. They receive more attraction. So they are bound to the nucleus. In such a case, the s electrons, which are more closer than p electrons, these s electrons are bound to the nucleus. That is why they do not participate in chemical combination. Okay, so that is what is given. The outer 6s electrons are bound to the nucleus because of poor shielding effect of inner localized electrons. Now we specifically mean those orbitals which are diffused. Which are the diffused orbitals? 4f and 5d. S and P, they are more sharp. Okay, they provide proper shielding. Whereas F and D, they are more diffused. That is why they provide less screening effect, poor screening effect. Now this makes the 6s electrons reluctant to participate. They are bound to the nucleus because of the poor shielding effect of these orbitals. So they are bound to the nucleus, so they are reluctant to participate. In such a case, only p electron will participate in chemical combination. That means Tl will show only +1 oxidation state because only this electron is lost. And on the other side, there is also another concept that goes for the same property. What is that? Say now you are having, I told you that Tl will exhibit +1 oxidation state. That means it will exist in the form of TlCl, right? Tl का +1 है, Cl का -1 है, so TlCl form में exist करेगा. Now what if TlCl3 exists? It is supposed to exist in this form, is it not? But it is existing in this form. Now what is wrong if it has to exist like this? Let us see. Now TlCl3, that means Tl shows 3 individual bonds with each of the chlorine atoms, right? Every time a bond is formed, energy is released. Remember, bond formation is always exothermic, bond breakage is always endothermic. Now, when one TlCl bond has to be formed, energy has to be released. Now, the released energy, now what is it having? It is having 6s2, 6p1. Now, this is how you write 6s2, 6p1. This is the ground state. Now, if Tl has to participate in the bonding process with 3 of the chlorine atoms, then this 6s has to unpair itself. It has to separate. Only then 3 individual electrons will be there which will participate in the bonding process. Okay. So पहले इस 6s जो paired electrons है उसको unpair करना जरूरी है. Unpair करने के बाद वो single electron होगा. Each and every orbital will now participating in the bonding process with the 3p electron of chlorine. Now, who is going to unpair the electron? To unpair the electron also energy has to be supplied because these 2 electrons, they have opposite spins and through attraction they are together now. Now if you want to unpair this, you have to supply energy. What they say, the amount of energy released after the first TlCl bond formation, if that energy was sufficient enough to unpair the 6s electrons, probably Tl would make 2 more TlCl bonds and exist as TlCl3. But the amount of energy released in the formation of the first TlCl bond is insufficient to even unpair the 6s electrons. Is that clear? So what they say, Tl is showing only +1 state. It is not able to show +3 state. Yes? So that's what I've shown here. TlCl bond formation is exothermic. Unpairing of electrons, it is endothermic. So the energy required to unpair the 6s electrons is not compensated by the energy released in the formation of the additional TlCl bonds. Is that clear? The amount of energy required to unpair the 6s electrons, it is so high that it is not being compensated. That is why Tl exhibits +1 oxidation state. So you say stability of +1 oxidation state increases down the group. So the statement stability of +1 oxidation state increases down the group. Why? If you are asked, you will say it is due to inert pair effect. That's it. Okay. Same way, in the case of group 14 also, lead, it exhibits +2 oxidation state rather than +4. In group 14, The number of valence electrons are 4. So it should exhibit plus 4. Instead, Pb is exhibiting plus 2 oxidation state. Why? Because again, it is due to the formation of, due to the effect, this inert pair effect only. It is also showing plus 2 oxidation state. It is having a configuration of 6s2, 6p2. Now all the 4 are not participating. 6s is remaining reluctant. So only p electrons are participating in chemical combination. So Pb exhibits plus 2 state rather than plus 4. So this is also due to inert pair effect. Okay. So whenever you get a question that down the group lower oxidation state is more stable, it is 2 units less than the group valency, immediately the answer is inert pair effect. That's it. Is that clear? For understanding, I told you all these things, that the amount of energy is insufficient, this and that. But as a question, if you are asked, then you just have to write it is due to inert pair effect. That is sufficient, right? Okay. Now, what other typical properties we have in this p block elements? Tendency to form multiple bonds. This is another important property which S block does not show. They make p pi bonds. Now this is what you have experienced or you have already seen with respect to nitrogen, why it is existing in the diatomic state and it is having a triple bond among the 2 atoms. Same way oxygen is having a double covalent bond. Same way you have ethene, ethyne. In all these cases you have pi bond formation. Not only among the atoms, you also have nitrogen, double bond oxygen, carbon, double bond oxygen. All these things are also known to you. That is all because of p pi bond. Why it is p pi? It is because p orbital of one atom is overlapping with the p orbital of another atom, resulting in pi bond formation. This is why it is called as p pi multiple bonds. Okay. Now this is a peculiar property which is specific to p block elements. S block and all, they will not show this. Okay. Now especially second period elements, they are more particularly showing this particular property. Now when you see heavier members, you will find they will show d pi p pi. That you will study later in 12th class. Right now it is enough if you know p pi bonds. Right.